Hi, I'm John. I'm the CEO of Veridise, and I'm here with Michael, a compiler engineer at Aztec. And we're going to talk a little bit about ZK in general, and more specifically the Noir programming language. Why don't we get started by talking a little bit about Aztec and Noir? Can you tell us about the Aztec ecosystem, and more specifically about the Noir programming language?
Yeah, so Aztec was created to address the insurmountable challenge of having private requirements of financial assets, but with a public transparent blockchain. And so this has taken 7 years, and there are a lot of different engineering requirements and conditions, and we've made a nonprofit in Switzerland, and we're doing a lot of these other steps to make sure that we can deliver a secure, private, and ready-to-use for business blockchain.
Okay, cool. And so, there already exist some ZK DSLs. So what was it that made you guys decide to make your own ZK language, Noir?
Yeah, definitely. So really, I think what the biggest pivot of why you would look at Noir versus other ZK DSLs at first is really the multiple backends. So what we've seen with ZK is that the proving systems evolve very rapidly, and differences with proving systems can be very stark. Like in one proving system, you might have recursion or folding. In another proving system, you might have a lot more ability to do bulk transactions, but not recursion or folding.
Okay.
And we do expect these to evolve over time. There's a possibility of quantum resistance in some of these proving systems.
Sure.
And really, we do expect them to change. So no other ZK DSL is prepared to move to multiple backends. And if they are, they tend to be extremely low level with a gate-based representation. Or they're really locked into a single Plonkish style table-based representation.
Okay, you mentioned something interesting there about if they are compatible with multiple backends, then they tend to be really low level.
Yeah.
And so let's pop up a little bit and talk about the language itself. How about the developer experience? One thing that we've seen when looking at a lot of these circuits is the fact that they're so level leads to a lot of difficult to reason about programs, difficult semantics, and that has led to more programming errors. So what can you tell us about Noir as a programming language for a developer? What's the developer experience like?
Yeah, so for a developer experience, we really try to get as close as we can to a Rust experience, because Rust gives you a lot of checks, a lot of guardrails, and it's now a pretty standard systems language. Now, some people consider systems languages to be too low level, but they aren't trying to use Python and get random type errors at runtime. So it really is about the level that you would expect for a circuit. And we try to hide a lot of the field-specific details, but also give APIs to expose them when needed for performance. So really, we want users to be able to just throw something together as a circuit, as a Rust-like statically typed language, and it just work. And then when they need more performance, they need more crypto, they need specific functionality for privacy, then they notice that it's ZK.
Okay.
Then they notice it's more of a DSL.
Sure. So let's drill into that a little bit. You mentioned that it's very Rust-like, but with a lot of these ZK DSLs, someone has to explicitly write constraints. They've got a witness generator, which is going to generate the program, and then they have to go and almost rewrite it again by encoding the constraints. And so is that similar to how the Noir developer experience is?
So you could actually go either way. So we have a unconstrained versus constrained, where you can explicitly write constraints. You can explicitly write the unconstrained version that will execute off the circuit, and then make sure you pin it back. But also, we offer a totally normal dev experience. If you write Rust code, all the types and size checks will ensure that the constraints are satisfied. And if you don't use any unconstrained functions, then we effectively cover that for you.
In effect, does that mean that if I have a variable x and I want to assign it to y divided by z, which typically you can't do in a normal DSL, you can do that here?
Yep, you would, just like a normal Rust program, you would say x equals this, y equals the division, and you can print it, you can constrain it to an output, you can do whatever you'd like.
Okay, that's cool.
Yeah.
You also mentioned the notion of under-constrained functions. Can you describe a little bit about how that works?
Yeah, I think I said unconstrained, but under-constrained is very closely related. Yes, because as soon as you have an unconstrained function, chances are it's under-constrained.
Sure.
So yes, an example that I myself have made mistakes with is sorting.
Okay.
So when we sort in an unconstrained manner, what we want to do is we give the array to the, send it out to the unconstrained version that will run as kind of like a sidecar. And that'll actually do the sorting and we give it back, right?
Yep.
But then we actually have to make sure that it was the same list of elements,
Yep.
that it's a permutation, and that it's actually sorted. So that's much, much more efficient than actually sorting.
Yep.
But if you don't do both of those steps in their entirety, or you have some mess up where you're not comparing properly, that's where the actual correctness is ensured.
Okay. So in this case, the unconstrained function is going to perform the computation, but really there is no guarantee that it's correct, and so then you have to add in constraints in order to make sure that someone actually encoded that computation correctly.
Yeah, exactly. It's somewhat like async programming, where you have a thread, it goes out, but it might error in the middle, and so you have to make sure that you actually got back what you expect.
Yeah. So sorting is an interesting way, or is an interesting starting place for this, just because there are some, sorting algorithms that can take a long time in order to compute. So you've got, I guess you could use an n-squared algorithm if you want, or something like that. But then in order to verify that it's actually sorted, you just need n time to do that.
Exactly.
So,
well, a little bit of overhead for the permutation checking.
Okay.
Yeah.
So we have unconstrained functions. We've got normal-looking computation. Is there anything else that Noir is bringing you that other ZK DSLs aren't?
Well, I'm not familiar with the complete ecosystems of all these other DSLs. I'm really proud of our tooling. We have a really cool language server protocol and VS Code extension, and we have flame graphs and other analysis. Step-by-step debuggers are usually impossible for constrained circuits, but we have a step-by-step debugger that goes through the if branches, and basically it goes through your program as you would expect to go step through a Rust program. And I think these are fairly unique in providing a more of a traditional developer experience for this.
So you've brought up tools. Are there any tools that you think it would be useful to have that don't currently exist in Noir?
Yeah, definitely. We just mentioned under constrained checks.
Yeah.
Definitely more ways to do that. Get very challenging very quickly. Everybody is concerned about performance, so continued tools to analyze and pinpoint performance concerns.
Okay.
One example is that flame graphs will not show you that you have a less than spread out through your program many times, because it won't be like a single call necessarily. And so you'll have like a bunch of little tips of your flame graph that are all less than.
Sure.
But the tool doesn't make it easy to see that.
I see.
Right. So better analysis for under constrained and just constraints in general, and then better tools for performance.
Okay. So specifically for the under constrained circuit side of things, that's because that is a very common security vulnerability.
Exactly.
And so at Veridise, we spend a lot of time developing tools in order to identify these things. And we actually do have a tool to detect under constrained circuits. But we've also, we've noticed a lot of other bugs that circuit developers tend to make. And so an example is someone just encoding the wrong computation and other things like that. So how do you see the ecosystem developing? Do you see space for other types of tools like fuzzers, static analyzers, and stuff like that?
Yeah, definitely. Fuzzers and static analyzers, I feel like, are the next step. We have a little bit of static analysis built into Noir currently. So you can do this. For example, there's an independent subgraph check, which is kind of like I completely forgot to constrain this part of the circuit. But yeah, additional static analysis would of course be super useful. And then we have a prototype, just throw spaghetti at the wall circuit fuzzer, and that is being replaced with an execution guided fuzzer. With these traces of the exact branches that are taken, we can do a little bit better fuzzing of making sure we take all the paths through the circuit.
Cool. Noir brings a lot of new features to a zk DSL that other programming languages don't necessarily use very much. And so one example of that is the metaprogramming that's built into Noir. Can you tell us a little bit about that and what it enables circuit developers to do?
Yeah, definitely. So when we were looking at metaprogramming, a lot of people were asking to derive instances of things, derive equality, automatically print things. That sort of thing. And really, they also want to do things like add privacy handling data or structs to an existing circuit, add admin functionality to an existing circuit. These kind of mix-in behaviors are most easily done with metaprogramming with currently. So we originally looked at doing a Rust-style metaprogramming, and an older version of Noir had pure Rust metaprogramming. So it was just an extension to the compiler in Rust. Our compiler's in Rust, by the way.
Okay.
And you would just write a bit of Rust code, it would manipulate the AST, and that would be it. But what we found was that created a large separation of concerns, where to audit a Noir program that used metaprogramming, you would have to audit both Noir and the Rust code, the Rust extensions. So what we came up with was a first-class citizen style metaprogramming, where metaprogramming is like a generic comp time anything, and it's all run within Noir at comp time as part of the Noir language.
Where comp time is compile time, I assume.
Yes, comp time is compile time.
Okay.
Yeah, so what this allows us to do is leverage Noir's type system, leverage Noir's additional safety abilities, and basically extend the language from within the language. So we have exactly what I mentioned: derive equality, derive printing, derive showing things, adding circuit, Aztec requirements for Aztec circuits, things like that. And there's a couple other things that we've done with that a bit different from Rust to make sure that things can still be parallelized, that there's not too many dependencies, that we respect privacy. And so we kind of can still have like a modular sane API completely located within Noir with metaprogramming that's auditable.
And I assume that part of the reason why you guys were really interested in doing this is to help improve the succinctness of ZK circuits, right? Because pretty frequently, metaprogramming is used in order to essentially reduce the amount of code that you have to write by simply saying, this is something that I want to derive, or this is something that I want to use over and over again, and I am just going to essentially manipulate the Rust compiler, and the Rust compiler is going to do my work for me. Is that the main reason that you guys added in metaprogramming, or is there anything else that you found metaprogramming helps you with?
So that was the original reason that people wanted to derive these repetitive boilerplate things for different structures and different data types, especially for testing. But I'm interested in some other applications. So for example, when people are debugging hash functions and encryption functions, and there's a bug, usually they're passing it into another circuit, or it has to get processed by another protocol. It's completely opaque. I'm sure you've seen this, that you're like, okay, the one hash is this digits and this other hash is completely different digits, and you have no idea where it came from. You're looking at like the individual bytes, you're checking low endian, high endian, right? You're doing all these checks, but basically from an abstract level, if you re-engineered the hash function into a fake hash function that was transparent, and if it's, you could either just pack your bytes in, potentially if you have variable length hashes, or you can just do an oracle. That we have these oracle calls to call out to the sidecar with unconstrained, as I mentioned. So basically you could have a fake hash function that's totally transparent. You know exactly where it came from. You know exactly the encodings of all the bytes. And this extension would basically just keep track of it for you. And so then you would have a metaprogramming annotation, fake hash functions, and it would replace all your hash functions with.
And so in that case, it helps you with testing and ensuring that the ZK circuit that you're writing is actually safe before you even get to the audit.
Absolutely. And so other ways of adding extra test code in the middle of your code that you don't want to maintain the two copies, but you're happy to let it run at compile time and generate a couple variations, I think is super useful for testing.
Sure. Yeah, I mean, it makes it really easy to do like regression tests at compile time and stuff like that. But okay, that's cool. So if I wanted to use Noir right now, who has the ability to use it? If I wanted to use it, would I be locked into Aztec, or can I use Noir regardless of the ZK circuit I'm writing?
Yeah, this is a really common question. A lot of people think that Noir and Aztec are pretty much the same thing, but Noir is completely agnostic to both backend and which layer 1 or layer 2 you're using. We have basically a metaprogramming tool called Aztec NR that adds in the Aztec specific requirements to use Aztec. But if you never import Aztec NR, you are agnostic.
Okay, so I can write a Noir circuit, and then I can generate a proof, and it can be verified anywhere.
Yeah, and what's really cool is because of the multiple backends, you can actually plug a Noir circuit into the middle of CIRCOM. You can plug it into the middle of different proving systems. And so really you can kind of mix and match and say, hey, Noir has ZK Passport. Noir has, zkTLS, zkEmail, like some of these really cool composable pieces.
Yeah.
And I don't have to be locked into Aztec or really even Noir itself.
Yeah.
I can just use it as a dependency
Yeah.
and get all these benefits. So I'm really excited about that.
Yeah, for sure. Yeah, the composability is very interesting. And it's going to be interesting to see how people use that in the future.
Yeah, definitely.
Yeah. So we talked a little bit about some of the things that can go wrong, but can you describe a little bit about the types of vulnerabilities that you're particularly worried about or anything
Sure.
like that? And then maybe we can, talk a little bit about how tools might be able to help with those.
Yeah, definitely. Two that immediately come to mind is sizes of things. I've spent quite a long time trying to make sure that all the sizes of things are consistent,
Okay.
specifically numeric generics,
Okay.
because numeric generics will control the sizes of your arrays, the size of your structures, these other things. And so if those sizes are wrong, you can read past the end of an array and just panic, right?
Okay.
Or you could end up being unconstrained because your algorithm doesn't apply outside of a scope of what you expect. Or actually there is a particularly nasty case where you would expect to have like 3 elements and to be the 3 hashes of your users. But if there was a bug, it could be 0.
Okay.
And then you wouldn't have any constraints
Okay.
because you would have no hashes.
Yeah.
So the sizes of things are super important with circuits because by the time it gets to the polynomials, that's where a lot of the constraints lie. And then secondly, really just generally optimizations. So in the type system, if you do like x plus 1, it'll do it to 2x plus 1, right? Those types of transformations are extremely complex and they have a lot of corner cases. And then basically we have the same type of issue with algebraic transformations when we're doing optimizations, not of the types and the sizes, but of the code itself.
Okay.
So when we're actually at like the assembly level and we're doing optimizations, we have many different passes to try to get the most performance out of a Rust-like language that ends up being a circuit, right?
Yeah.
So each of those have specifications, expected context. They make assumptions about prior passes. These sorts of generic...
Yeah, that's interesting because you're talking about like optimizing code, but obviously a developer wants to make sure when they write their code and they've written it correctly that any optimizations aren't going to break that. So have you done any work to try to make sure that like your optimization passes are proven and valid?
Yeah, definitely. We've started the work, but basically we're ramping up fuzzing.
Okay.
On specifically the optimization passes. For the type system, I actually was able to come up with a solution where we keep track of the original version. And because everything is monomorphic by the time it reaches the circuit level, we can just evaluate that expression and make sure that any transformations were correct.
Evaluate to the same thing
Evaluate
for
to the
fuzzing.
same- yeah, because it's all constants.
Okay.
But when we are doing like the optimization passes, we need to do more fuzzing basically.
Okay.
And like turn passes on and off. Some of this testing has already been done, but some of it is ongoing.
Okay. For some of the transformations that you described, it sounded like they were basically peephole optimizations, so they've got a very small context. Have you considered using something like formal verification, using SMT to actually verify that the transformation itself, like the transformation being performed is correct rather than like this instance of the transformation is correct?
Absolutely. So I feel like that's kind of a next step for us to take, and that's why I'm happy to be talking, because you guys are really, really good at the SMT stuff. So I feel like, yeah, exactly. When you have like a peephole optimization and you have like these really specific transformations, then yeah, that's exactly where SMT falls in. But if you have something like our constant folding pass needs to evaluate whether or not there's a predicate, or evaluate whether or not there's a side effect, ensure purity when needed, make sure that there's no mutability, right? And then actually do a full interpreted evaluation with extra checks, basically.
Yeah.
That I feel like would be a little bit more challenging to verify, and we're going to rely more on fuzzing.
Okay. So let's go back to the security vulnerabilities. So like at Noir, you guys have obviously thought a lot about users. You've tried to make it difficult for people to write like bad circuits by like having unsafe, pointing out when people are writing unconstrained or invoking unconstrained functions and stuff like that.
Right.
But you know, what are the types of bugs that you're worried people will make, like the developers themselves?
Yeah, honestly, a lot of them start to revolve around privacy.
Okay.
So privacy is very complex in a ZK system as opposed to Web 2, because in Web 2, privacy is we don't expose an endpoint.
Sure.
You know, maybe we don't even expose it to the internet, right?
Yeah.
Like, or you encrypt it really, really well with a very standard encryption method, right?
Yeah.
But here we have a lot of users don't realize when they're rolling their own crypto.
Okay.
Right, they use a part of one crypto primitive and part of another crypto primitive, but they're not using the whole protocol and then the whole next protocol. And so it can be very hard to tell with these systems, am I secure?
Yeah.
Is it private? Have I used the crypto correctly? Am I leaking entropy somewhere? And then, you know, just understanding the life cycle of such an application, I think is challenging for developers that haven't experienced it.
So let's go back to the entry point, because at Veridise, there's a couple of different types of privacy leaks that we've seen. So there's kind of the traditional privacy leak, which I think you touched on a little bit, which is someone has a private input and it somehow flows to a public piece of data, so like a public output or something like that. And that's one very explicit privacy leak that we can find pretty easily using tools. And at Veridise, we've built tools to identify those privacy leaks. But you also mentioned entropy. So can you describe a little bit about how entropy could be used in order to expose private data?
Yeah, definitely. So two things come to mind. One is people like to use PRNGs in these protocols to have deterministic randomness, but they often use secret information for those PRNGs. And the PRNGs are often not CPRNGs, cryptographically secure, or I don't remember the exact acronym. But they're usually not cryptographically secure PRNGs, and then they effectively leak a couple bits or a couple bytes of that private data. So that's a common case, but also you could really just have a private input, compute on it, and then say like, oh, well, we have the length of it, or we have some other things, and those end up being public. Because they're indirectly computed, it's very hard to tell how many bits of entropy are leaking. And if we have many, many samples of an execution of a circuit, we can start to reconstruct kind of the point cloud of the hidden data. Yeah,
for sure. So yeah, I thought that that's very interesting that you mentioned length. So, you know, you have to worry about the attributes of the data that you're exposing, but then also you mentioned another thing at the end, which is, you know, kind of another thing that we found, which is the many data points being able to be kind of consumed in order to reveal private data. So one thing that we've seen is, you know, people commonly use things like nullifiers in order to, you know, expose that this set of public inputs is unique and therefore my proof should be accepted. However, one thing that we've seen is a lot of people will use like hash functions to do that, and they won't necessarily consider including something like nonce. And so in that case, for particularly common types of values, like 0 is 1, 1 is another one, you know, what you see at the end is the exact same hash over and over again, and then someone can easily tell using like a dictionary attack, oh, this is your value.
Right, and then if you're using the same hash over and over again, eventually you expose yourself to like rainbow tables and brute force, right? You know, I remember the XKCD, I have a random number, it's 4. I derived it securely, but now it's fixed.
Yeah, so I guess Noir is specifically built in order to, you know, kind of help people create these private computations. And so are there any, you know, kind of guardrails that you've put in to help people protect against these privacy leaks, or to make it a little bit more clear when they might be leaking data?
So I think it's actually pretty challenging. I think we do have a static analysis check that if you directly put a private input into a public output, you know, we'll say, oh yeah, this is obvious, you copy pasted it into the wrong place. We'll at least throw a warning. If we haven't built that out, we have plans to do that level of analysis. But after that, it gets a little bit fuzzy, pun not intended. There are some data flow analysis tools, but I haven't seen them like applied to field elements. And basically there is some more traditional research on making sure that you don't exactly leak entropy through your public entry points. We've only started looking into this more carefully, and mostly what we've done is made advice of people not roll their own crypto, and tried to point them towards the standard methods of protecting this data.
So how common do you think these types of vulnerabilities, will be? Like, how worried are you about them, I guess?
Well, the data flow stuff, since we don't have a very clear way to do the analysis,
Sure.
the likelihood of it occurring, I think, over a long enough time period is 1. There's a bit of a question of what types of data this will be used for, and what levels of concern people will have for that data, right? So for example, with health or legal data, you might have a much larger liability and you would have to do a lot more steps, but they would already be doing audits, right?
Yeah.
Whereas if somebody's just doing like a Twitter clone real quick, and it's just like a hackathon project, they might have some leaks, but they might not care, right? So I feel like in the middle, where people don't have a huge budget to check for these things, and it's not a throwaway project, it's not super clear.
Sure.
How much will people care about leaking their data, and what will they really be using this for?
Yeah.
If you use this mostly to scale compute, you can leak some entropy because you're mostly concerned about just separating the data from the compute.
Yeah.
You're probably going to join them up later.
Yeah.
So I think there's definitely a question of how big an issue it will be, like practically, but I do think it will occur
Sure.
quite a few times.
Sure. Since we're on the topic of privacy and zk, I think it might be interesting to talk a little bit about like zkVMs, because with zkVMs, they kind of have, they typically require more resources, and right now people are particularly interested on running zkVMs on proving networks, and so that has a lot of implications for privacy. And so, can you talk a little bit about the differences between Noir or zk circuits developed with Noir and zkVMs and some of the privacy implications there?
Yeah, so I haven't really seen a lot of zkVMs that actually have a lot of privacy built in. So I can't speak to exactly the comparisons on privacy there.
Sure.
But I can say that if you're rolling up large blocks of transactions with a zkVM, then you're likely just shoving things in without caring how closely it matches the circuits. And so there is a question of kind of like the individual zkVM maturity. And it's how much have they fuzzed? How much have they checked their specific sizes of everything? They are usually EVM-based zkVMs, right? Or it's RISC-V, right? The most two popular ways, right? So both of those have a very strict control flow, and they don't closely match circuits. So you can scale if there are some cases that use GPUs to scale to really, really huge computations. And then that's kind of like the trade-off. Do we want to throw the whole kitchen sink in and use GPUs and try to just like chug ahead? Or like, do we need to run on user devices? Do we want to be a little bit less centralized on a specific proving network? And then really, do we want to really specialize to our particular case?
Okay, so let's hit in on that a little bit more. So the device proving versus, kind of the proving network proving. So can you speak a little bit about who might want to make a system that would prove on your device versus a proving network?
Yeah, definitely. I think a easy recent example that we have is we have zk Passport on Noir. And zk Passport allows you to use the crypto in your passport that already has a root of trust and has like these certificate signings. You can basically trace back to the root of trust for your country and prove in a Noir circuit on a user device that their passport is valid and is connected to their address. Okay, you wouldn't want to do that with any of the existing on-server cases, right? You wouldn't want to send your passport to the server and then trust that it's going to get hidden by the time it gets rolled up.
Right.
So really cases where you have completely private inputs and the user doesn't need to ensure that there's a copy publicly available to the business, which can be required for certain regulations. That's, I think, where it's much more interesting to run it on the user device. And even without privacy, there are some cases where basically people just run with it and they run the proof on the user device. And then they are able to do some blinding. But those systems are not built for privacy, so they're not audited for privacy. So yeah, I know you guys do a lot of SMT, and it can get really, really sophisticated. You guys have published several papers in major conferences, and definitely written a lot of code.
Yeah.
So my question is, for an average developer, somebody who's a little bit less familiar with formal verification, how do they tell at just a high level, is this likely to be a very difficult problem for SMT,
Yeah.
or is this likely to be something we can just, chug it?
That's a good question. It is sometimes difficult to tell because SMT solvers can be very opaque to the user, because really what an SMT solver is going to do is it's going to take in just a mathematical formula and it's going to attempt to solve it.
Yeah.
And so really the SMT solver doesn't give you a whole lot of feedback about what's going to work and what's not going to work. And so it will either return, yes, I solved it and this is the solution, or no, there's no possible solution to this, or unknown.
Right.
And the unknown case, I think, is the part that you're specifically asking about, because it's the most frustrating case that people encounter with SMT. Yeah. And so there are some things that SMT struggles with. So one particular thing is SMT really struggles with nonlinear equations. And so that's one of the difficult parts about using SMT with zk, because zk uses so many, like all of the constraints that you have in zk could be nonlinear. There are a lot of nonlinear equations in there.
Definitely.
And so that makes it very hard to scale with an SMT solver. But also the other thing that makes it difficult to scale is just the size of the formula. And so one thing that you'll notice is as your formula gets bigger and bigger, the SMT solver starts choking more. And it could have to do with simply the number of constraints that you now have to satisfy, but sometimes it doesn't seem to be related to that. And so it can be really frustrating because you kind of have to work around this in a lot of different ways. And so at Veridise, there's been several things that we've relied on to try to, let's say, work around the SMT solver. And so one thing is it's often difficult to just throw an entire circuit at an SMT solver because of the nonlinear the fact that you've got so many nonlinear equalities.
Yeah.
And so instead, what it makes more sense to do is to target your SMT queries. And so to use, basically what you want to do is use a variety of techniques and only use the SMT solver when you need to.
Yeah.
So for example, in the PICUS paper that we published, essentially the way that we got around using the SMT solver to determine whether a circuit is deterministic, which you do by saying, I have this fixed assignment of inputs and are there multiple assignments of outputs, like you can encode that as a formula.
Right.
But you can also use other techniques to help you reason about whether or not a particular variable must now be deterministic.
Right.
And so you can do that. In the PICUS paper, we talk about it using static analysis. Because for example, if you have a linear equality, and so let's say you just have an equality like a minus b equals 0.
Right.
That's a very familiar equality constraint.
Yeah.
And so if you know that A is deterministic, but you don't know if B is deterministic yet, obviously you can now say that B must also be deterministic.
Right.
And so by having this kind of interactive way of using static analysis and SMT to make progress forward, you can now start proving more interesting properties and properties at a much larger scale because you're no longer just relying on the SMT solver.
Right.
And so one thing that we found a lot is that we have to use, kind of complementary techniques, particularly when it comes to zk, in order to scale things like formal verifications to real zk circuits.
Oh, that's very cool. Immediately I'm thinking, so if the zk DSL, for example, that you're doing this analysis on with PICUS, was able to give you a little bit more metadata that, hey, these are the only dependencies, hey, this is a pure computation, there's no side effects, you could probably enhance that analysis a bit.
Yeah, definitely. So we have had to come up with a lot of, kind of patterns that we know can check determinism or, show determinism statically. And so the more information we can have from the compiler, let's say, about values that a particular variable could take, the better. So one example of that is when you are at the level of constraints, everything is a field. You don't actually know the type of any of the variables.
Right.
And that becomes a particularly big problem when reasoning with SMT, because you can actually kind of also enhance the SMT solver by knowing the type of the values, because then you can do things like case splitting and stuff like that.
Yeah.
And so one very common thing that we need to do, or that we have done with Picus, is try to determine when something is performing like a range check or a bit decomposition,
Yep.
and recognizing that pattern so we can, kind of reintroduce types back into the program,
Yeah.
and then use those to help the SMT solver and the static analysis make progress.
Yeah, it's interesting you mentioned using a small amount of a field that has a ton of bits and wanting to retain that.
Yeah.
That is one of the causes of slowdowns that we're currently addressing.
Oh, really?
Yeah.
Oh.
that we default to the full field element.
Yeah. Yeah.
Because we want full support, full security, and
Right.
and basically we need to emulate smaller field elements in the cases where we know it's smaller,
Right.
to get a little bit more performance.
Okay.
And then secondly, we do keep very close track of the sizes of all of our elements.
Yeah.
And I added some extensive bit size checks, basically.
Yeah.
So hopefully, we could work together to
Yeah,
to feed
definitely, definitely. And we're currently working on an intermediate representation for zk. And part of the reason why we wanted to do that is so that, one, we could have an intermediate representation that actually works well with our tools. So it's specifically targeting the ability to be analyzed. And so one thing that we're doing with that is trying to allow people developing zk languages to add additional metadata like this, these hints that can be used by LZK, which is then passed on to all of the tools that we're developing as well.
Yeah.
And so I think that there's certainly a lot of opportunities for us to collaborate and see some of the attributes that you guys have needed to add in for performance, because likely a lot of them will also help us with the ability to either verify or find bugs in the zk circuits.
Yeah, absolutely. As we pin down the specification more and more, we can have more tight implementations, and we can kind of iterate on that process.
Right, right. This has been a really interesting conversation. We've touched on a lot, and I feel like I've learned a lot. And thank you for being here to talk with us and to share some of the knowledge that you have gained while working on Noir.
Likewise, I feel like I've learned a lot this conversation. Thank you for having me, and I look forward to working together.
Yeah, me too.